right, welcome everyone. So this next section is going to be presented by Greg Lytle, and he's the Ozone VP of Engineering, okay? Responsible for imaging products and services for embedded platforms. And so he's going to talk about, can you put one of these networks on a $3 device? I find this actually fascinating. I actually work on some of this stuff myself, trying to take networks and putting them on much lower cost devices, because I mean, you're not going to be flying your drone around with a cluster of GPUs on it, right? So anyway, so take it away.
Thanks very much, Doug. So first, a little bit about Ozone. At Ozone, we build development tools and IP for helping customers enable edge-based machine learning solutions on a wide range of different hardware platforms. So let's imagine you're sitting in your office one day and the director of product management comes in and asks you to implement the same food classification network that you developed last year on your company's $5,000 smart oven. But this year they want to extend that feature across the product line, including the $150 toaster oven that your company sells. So how are you going to do that? When considering embedded machine learning solution, you need to look at your network complexity, how much memory that might consume. You've got to determine how you're going to implement your camera interface. You need to consider power consumption in some cases, and in this case especially, you need to understand the cost. Fortunately, there's lots of good solutions out there to look at when considering an image-based solution. There's SoCs based on FPGAs, there's CPU, GPU combinations, DSPs. You could roll a custom ASIC. You could look at one of the new vision processors. But today we're going to consider whether it's practical to do this on a low-cost microcontroller. You might ask the question, is this practical and why do you care? Well, not every application requires an extremely dedicated architecture to implement. If you're trying to do something relatively simple, cost and using a relatively common technology might be more important to you. Your design team is probably familiar with microcontrollers already. Probably you use a microcontroller on your existing product line. You also have an existing supply chain that you can leverage if you're using a common microcontroller technology rather than going to something that's more esoteric. So the incremental cost is also, might be relatively low because you need to add a camera to your device and probably upgrade the memory. But other than that, your design might be fairly similar to what you already have without embedded vision. There's obviously some significant performance constraints when considering trying to implement a design like this on a small-end microcontroller versus a higher-end SoC. Here's a graph showing the relative memory and processing capability of an Cortex-A9 CPU versus a Cortex-M7 with external memory or a Cortex-M4 with internal memory. In this particular example, we're going to try and focus on hitting that M4 design. The a $3 price point for a micro might be a little bit variable depending on your product volume and what you consider part of the micro. But in this case, we're going to try and hit on that M4. This particular M4 has got 256K of RAM and 256K of flash. And you need to implement the balance of your system in that same microcontroller as well. So we're going to dedicate about half of that to the embedded vision application. So the network design is one of the first things you're going to have to consider in addition to your data set. Maybe you've got an existing data set that you've used in your last product, or you're going to have to create your data set for the particular problem you're trying to solve. You might capture a number of images. You might look at synthetic data sets to augment that and improve your quality. Then you have to come up with a model. You have to train that model, analyze the performance, look at what kind of device that will fit on, and most likely iterate that process until you get a reasonable balance between price and performance. When looking at the different network types you could implement for a vision application, typically there's different layer types, so it's good to have an understanding of what the resource constraints are for those layer types. You can look at fully connected layers or dense layers and convolutional layers. So first, looking at a fully connected operation, you'll need to implement a buffer for the input RAM, in RAM for the input buffer of a layer. You'll need an output buffer, and you'll need the weights between all the connections. So in a fully connected layer, every input is connected to every output. So the number of weights learned weights you need to support in the design is the size of your input buffer multiplied by the size of your output buffer. The number of MAC operations is similar. It's equal to the number of connections. So it's the input size multiplied by the output size. In this case, you can see if we implemented this with 32-bit floats, we're going to exceed our flash size by a large margin. So one of the obvious optimizations is going to quantized 8-bit weights for your network. In a convolutional operation, your weights are shared, so it doesn't require typically as much flash. So you'll again need to implement a RAM buffer for the input, a RAM buffer for the output, and the weights in flash which are equal to the size of the depth of your input buffer, the size of the convolution kernel, and the depth of the output buffer. You'll need a data set, as I said, to train your network. In this case, I don't have a food classification data set, so I'm going to use a German traffic sign data set, which has about 40,000 training images, about 12,000 test images, and it's broken up into 43 classes. Obviously, this doesn't have much to do with classifying food, but it's a reasonable representation of a typical network that you would apply on a constrained application. Now you have to consider what kind of network would be reasonable to support on this kind of device. Obviously, you're not going to put Inception on a small-end microcontroller. I think the size of exception is about 100 megabytes. So if we're trying to fit in that small memory model, we've got to look at a smaller network. In this case, we're starting off with a network with 3 convolutional layers and 2 dense, fully connected layers. We might fit in our model size for our RAM, but you can see that the flash size exceeds what we have available internally on the part, so we're going to try and optimize that. We can eliminate one of the fully connected layers, go through the training process, and see what kind of results we're getting. In this case, by eliminating that layer, we've reduced the flash size from 2 megabytes to 200K, and we've lost about 2% accuracy. I didn't really point it out, but on the last model, we were getting about 95% accuracy. We can also look at a fully convolutional network with no fully connected layers. The advantage of this, again, smaller flash size because of those shared weights. So now we're getting down to 100K of flash, around 72K of RAM. And our accuracy is around in the same ballpark. But it's still useful to look at whether we can further optimize this, particularly looking at the number of multiply accumulate operations. So the first step I did was eliminating one of the convolutional layers in this network and reduced the flash size in half, retrained, and lost about a percentage of accuracy. I then looked at what can I do by reducing the depth of a few different layers in this convolutional network and knock the flash size down by 5, reduce the RAM size, and more importantly, also reduce the number of MAC accumulate operations from 2 million to 200K. This dropped my accuracy from 93% to 91%, but that might still be reasonable for this kind of application. Now you've got to consider how you're going to target this trained network onto your microcontroller, your embedded target. You could take the output of your training tool, maybe you've used TensorFlow or Caffe, you could extract the weights, and you could write some custom C code to implement that in your microcontroller. That would be highly optimized, but maybe not quite as flexible as using one of the vendor tools. So there's a number of vendor tools out there that will take the output of TensorFlow or Caffe and target an end device. The advantage of these tools is they support different types of networks. You can iterate more quickly. You can profile on the target device. And in some cases, you can look at incrementally updating the model on the target device as well. Some of the challenges you have to address when looking at one of these constrained devices is how you deal with the fixed memory allocation. So you don't have malloc or an MMU on these devices, so you need to fit in within your memory model at compile time. You also have to consider the memory footprint on these devices. Often on a microcontroller, the memory isn't contiguous. So matrix operations need contiguous memory to be implemented efficiently. So you need to fit your matrix multiply operations into one block of memory. It's also important that you consider buffer management. You can't have dedicated buffers for every layer in your implementation and fit it within these constrained microcontrollers. So you need to be able to know when the memory is no longer required and reuse that memory. You also have to consider your sensor interface and frame buffer and optimize that process. And lastly, how are you going to validate on your constrained device? You need a mechanism for feeding images or validation on your target to check your accuracy. So first we'll look at the memory optimization challenge. In a linear network, it's fairly straightforward in that each layer can be destructive and reused after the subsequent layer is started. So as you're going through your network, the RAM buffer size is equal to the largest layer in the network. If you have a nonlinear network where one input goes to multiple branches, you need to keep track of the source buffer before you destroy it and reuse it again later in your network implementation. Here we're looking at the image sensor resolution and the impact that has on memory. If you look at the example of a VGA sensor, the available frame buffer would exceed the size of the memory on the target device. So you're either going to have to use the sensor at lower resolution or use a sensor where you can bin or scale the output and only use a portion of that resolution of that sensor. So again, you typically don't need super high resolution images going through a neural network to do classification tasks. You also need to consider the memory buffer copies for your image buffer. It's best to try and leverage the DMA in the part. You can further optimize some designs by going to a monochrome sensor where color isn't important. So we've implemented these different networks on a number of different constrained devices. I've picked 3 representative devices, an IMX6 from NXP, which is a Cortex-A9 running at 1 gigahertz, an RT1050, which is an M7-based microcontroller with external memory, and an M4-based microcontroller with, again, the 256K of internal memory. So you can see the original fully convolutional network that I picked, the FCN network, takes about 170 milliseconds to run on this design on the M4 controller. And then the optimized version takes about 30 milliseconds to run. So fairly reasonable results for this size of network. Looking at the accuracy across the different platforms, we get equivalent accuracy, which we'd expect because the inference engine encoder running on the devices is binary compatible. So what other areas can we look at for further optimization? Well, one is to, in this case, we're doing the matrix multiply math. We're implementing it in 32-bit float value still. So you could look at an 8 or 16-bit optimization for the math on the controller and fit into a smaller footprint. That requires more development time and effort. You could also look at supplementing the limitations on your edge-based inference with a cloud solution if you've got network capability or connectivity. So I've got a little demo here. If we can make this work. So So I've got my laptop connected to the Cortex-M4 development board over an Ethernet interface. Here's my data set in my tool, which is using, there's my network configuration again in my Deep View tool, which I can validate. We then go through the validation process on the desktop. So this will take our network, run through our 12,000 test images of our network, and give us an accuracy result and a confusion matrix. So the confusion matrix is helpful for looking for errors in your data set, where you can see which samples passed, which samples failed, and further diagnose either your data set or your network. So next I'm going to connect to the target device. Did I lose it here? There we go. Okay, we're going again. So I select the IP of the target device. And hit validate. It's probably a little bit hard to see here, but you can see the inference time, which is 30 milliseconds. It's streaming images, in this case, from my laptop to the target device. It's performing the inference on that target device, and it's reporting back the results. I can pause and look at specific images here as well. This is a view where the profile from the inference running on the target device is shown, and we're profiling different layers of the network that's been implemented using our tool. So you can go in here and you can look at which layers in the network are consuming the resources, the total resources on your implementation. So in conclusion, it is practical to implement a constrained IoT vision application in a small microcontroller. You need to carefully look at your network design in context with your data set and do proper optimization to fit it into the footprint you're trying to achieve for a given accuracy. You'll have to look at memory optimization techniques to fit it in the constrained memory. The specific part selection is going to be driven by those accuracy and performance criteria. So if you needed a larger network for this particular application or higher accuracy, you might have bumped up from the M4 to the M7 microcontroller to gain that extra performance. And you can leverage development tools, such as the one I've shown here, to help the design process and reduce the risk of implementing these kinds of designs across a wide selection of hardware. We've got a demo down in the Ozone booth at booth number 802. So if you've got any further questions or want to see some demos on these kinds of platforms, please come down around and check us out. And there's some additional resources here if you want to look into some further research on the area. Thank you very much.
Questions? Come up to the microphone here, please.
So why wasn't the looking at FP16 and int8 or the data formats one of the first things you looked at when looking at microcontrollers as opposed to the other pruning techniques that you employed?
Basically, we wanted to be able to support a wide range of platforms, both very small constrained devices up to larger devices. So we have a model that will run across any of these devices. So we look at using 32-bit floats first, and then if we need to do further optimization, looking at integer math after that. So in this case, the performance was acceptable without going to the further optimization of integer math.
Okay, thank you.
Okay.
Great presentation, thank you. If you could add one piece of hardware accelerator to your microcontroller, if I was a microcontroller guy,
Right.
what would it be?
Tightly coupled memory is probably number one. So often these devices are not so much CPU bound as they are memory interface bound. So we found significant improvements with tightly coupled memory. Now, going beyond that, an efficient matrix multiply hardware is probably the next key piece.
Ask another one?
Sure.
Quick, and what about RNNs and LSTMs? Is there a different architecture, different memory configuration you need?
Not specifically, like we can support those right now using our tool, but it's just implementation specific.
Great, thank you.
Okay, you're welcome.
Hi. Is there any room for parallelization on microcontrollers that you could look into, or other platforms that might let you run some kind of parallel operations?
Yeah, I think parallelization is more suitable for an FPGA-based SoC, where you can parallelize certain processes. And
It's not conducive for microcontroller environments.
yeah, I think you can get virtual parallelization, but effectively the microcontroller can only do one thing at one time.
Yeah.
So the other option is to go to a multi-core SoC.
Yeah, multi-core.
So we support SoCs right now with like 8 cores and GPUs. So you can partition your problem across the GPU and across the CPU and achieve parallelization that way as well.
Have you also looked into running this on DSPs? And if you did, what was the difference in performance?
Yeah, the DSPs, we've got 2 implementations, a C-code implementation and OpenCL implementation. Yeah. So we can compile across into different architectures. So really it just comes down to which is more optimal on that DSP, the C-code implementation or the OpenCL. Obviously the highest performance is the closer you can get to hardware. So there's a trade-off between being generic and being very, very tightly focused on the hardware architecture. So, the best performance is always going to be looking at the specific hardware architecture and optimizing for that.
Okay. All right.
More questions? Yeah.
Just one question. So for training, are you also running on this processor, or you're running on a different processor?
For training, we're running on the desktop platform. So we're using TensorFlow in the back end for training, and then we're extracting those weights and downloading them to the microcontroller.
With the same model, right?
With the same model, yes.
All right. Thank you.
Yeah, you're welcome.
Further questions? Questions? All right. Well, thank you very much again.
Thank you.